All right, morning everyone. I would like to begin this talk by acknowledging that this conference is taking part on Wiradjuri country. The Wiradjuri traditional lands are vast and stretch far to the south of where we are gathered today, to include a place called Walla Walla, where I spent my childhood. It is understood that Walla Walla was derived from the Wiradjuri words Willan Willan, meaning place of many rocks, an appropriate location for a geologist to spend their childhood. So I'll begin today's talk by thanking Wiradjuri people for looking after the entire Wiradjuri country for the past 70,000 years. Obligatory forward-looking statement, I refer potential investors to the company website. So today I'll take you through the geology and mineralisation controls of the GRE46 deposit, and then I'll hand over to Malai, who'll take you through some of his work he's been doing on volcanic facies architecture in the Cowal complex. So we just saw this map in the past talk, so I won't dwell too much on it, but you can see where the Cowal gold operations is located, and we also have Marsden down there in the Junee Narromine volcanic belt. Zooming into a camp type scale, you can see the Cowal igneous complex here. It's bound by the Boubrai and the Marsden fault. In the northern section, we have the gold corridor with GRE46, E42, E41, and E40 deposits, which we classify as low sulfidation epithermal deposits. In the southern Cowal igneous complex, we have the known Marsden calc-alkalic copper-gold porphyry, and we have E39, E43, and milli calc-alkalic prospects. Just an overview of the mine site reserves and resources. Evolution acquired Cowal gold operations back in 2015, and since then, bit of talk on that one. Yeah, since then we've grown the reserves and resources significantly, and that is no small part to the GRE46 underground deposit, which contributes 2.8 million ounces to the resource and over 1 million ounces to reserves. This is a cross-section through the actual mine site and shows the E42 deposit, and you can see in the black dotted outline the E42 pit outline. So E42 deposit is hosted within a sequence of gently to moderately dipping, openly folded volcanics and volcaniclastic sedimentary rocks. And they're intruded by a fractionated diorite and monzodiorite. So you can see in the yellow, that's a more fractionated core to the pink diorite rock. And to the top right, you can see GRE46, and that's separated from E42 by the Glenfiddich fault, which is a late offsetting fault, and we're not sure of the length and direction of that offset at this time. And a big part of Malai's work is reconciling stratigraphy either side of the Glenfiddich, but also across the Cowal igneous complex, where there's a number of these deep-seated offsetting faults. This is a planned section through the GRE46 deposit. Again, we have the late offsetting Glenfiddich fault, and we also have the Manor and Ardberg shears faults, as well as the Galway faults. These are low offset faults, multiple reactivations, and they're interpreted to be active during mineralisation. We look at the deposit in two separate halves. In the southern half, we have these Galway faults or splays, and the Dale-Winnie andesite butting up against the diorite contact. In the north, we have the trachyandesite unit, which is bulk mineralised, and you can see through the through the red dashed line, that's our mineralisation at GRE46 at this RL. Just forgot to point out, for the next few slides there, we're going to look at this section across the southern half of the deposit, which is outlined in the blue dashed line there. This section has been taken because it demonstrates most of the controls that we think are important to mineralisation at GRE46 deposit. The first one of these is preferential mineralisation of lithological units, and in this section, that's the Dale-Winnie down the bottom here. This is a brittle unit within the more ductile sediments and tends to fracture more readily to give us better mineralisation. In other parts of the deposit up north, that's the trachyandesite, not a local scale, pre-mineralisation in place dikes also show preferential mineralisation. And that also relates to rheological contrast, but an overall arching control of the entire deposit is the diorite and the sediment contact along the length of the deposit is the big rheological contrast. The diorite shows a lot of resistance to deformation, and we have these sediments crashing into it, which relates to the next point, which is the architecture of the diorite contact. You can see in the red outline of mineralisation where we get these overhangs and embayments in the diorite, we get a much wider mineralisation intercept than we do on, say here, where the Galway splay label is, where we have a more planar contact. And the last ingredient we need throughout the deposit is proximity to one of these low offset faults that provide fluid focus through their increased permeability. I'm just going to show you a few examples of some mineralisation from GRE 46 in the south. The first one will be from this hole up the top that goes through an overhang and into the diorite on the Galway splay, part of 19 metres at 10 gram intercept. So highlighted there by that yellow box, we have Galway shear mineralisation. I'll just draw your attention to the significant change in grade in those 2 metres. The Galway splay typically is not mineralised along the entire strike of the fault. However, you do get considerable mineralisation within it, but what is equally important is these small dilational veins surrounding these structures that provide significant gold ounces to our reserves and resources. Next example of mineralisation I'll show you is from the Darwini unit. It's part of an intercept that was 61 metres at 3.7. In this section, I know it looks like we're drilling down the Darwini unit, which we were, but as you can see here, we hit the veins at a pretty good angle. These veins, compared to the Galway veins I just showed you, have a high concentration of pyrite. And this is pyrite stockwork stringers, so that's a more intense example of mineralisation from the Darwini. And what that's showing you is it's supporting our theory that the Darwini within the more ductile sediments really breaks up and really allows that mineralisation to occur. And what you can also see in this image is mineralisation is leaking out into the host rock, which doesn't happen to many lithologies at GRE 46. It's pretty unique to Darwini. And this is just a nice image. It shows the same stock-wet stringers that are cut by a later vein that also has some chalcopyrite coming in, probably due to a pressure differential as the dilational vein opened or evolution of the fluids throughout the mineralising event. So this is just back to the cross section. We're now just going to look at a few examples of mineralisation from the northern section of the deposit within the trachyandesite unit. So as we move into the northern section of the deposit, we interpret that Manor and Ardberg faults are contributing more fluid focus than the Galways, and Galway and Darwini mineralisation tends to drop off as you head up to the northeast. This is just a couple of core trays from deep RLs within the trachyandesite. You can see some pretty intense silica, sericite and carbonate alteration down there. And typically, the more veins you get, the better grade you get. So you can see this is also a peperitic lava up in the top tray, coming into a more coherent lava in the bottom tray, and on that margin we're getting some pretty good grades. Just a close-up of some of those veins, you get dilational veins and some more stockwork fracture veins, and there's some pretty decent grades. Up in the higher RLs with the lava, we get more of these, for want of a better term, we call them on-site QSBs or quartz sulfide breccias, but they're really multi-stage veins that are polymetallic, and alteration in these higher RLs is more restricted to the halo around these veins and is possibly more feldspar dominated. We need to do more work in this area, but we think it's more feldspar dominated up in those higher RLs. As I said, they're polymetallic. You get heaps of pyrite, chalcopyrite, galena, and sphalerite of varying colours. And that's just what these large structures look like in core. You can see the contacts there are perpendicular to each other. We've got some late shearing, chopping off one of the boundaries there. Nearly out of time, so I'll just skip that one. I just wanted to emphasise how important it is not to only have good geological models, but also good geological foundations to put into those models. This is just a small example of that. So we split our deposit up into 19 separate sections and create stereo nets that are regularly updated on each section. This is just a subset of 4 of those stereo nets. You can see in the southern areas, we've got mainly sets of veins that are predominantly parallel to the diorite contact end or the Galway shears. At deeper RLs, you get a Dalwhinnie set of veins coming in. As you move further north, you get more of a southeast or even an east-west set of veins. These east-west set of veins up in this top right-hand stereo net are those large QSB or multi-stage veins that I just showed you some examples of. And you also get a flat set of veins, so you can't always drill optimal angle to all of your veins. And just a nice example of some late offsets. We get plenty of shuffling and reactivation of all stage veins and structures with low offsets and stacking throughout the deposit. I'll now hand over to Malai.
Oh, I did have a title slide, but I'd just like to say hello everyone, my name's Malai, and it's a pleasure to be presenting here. I'll just talk about my project to establish the problem with this volcanic architecture project. On the right is the latest revision to the geology interpretation that was done by Evolution. So that was completed just as I started the project in December 2020. On this map, the E42 and GRE46 ore deposits are there. And these red lines show the northeast dipping Cowal shear to the left and the steeply west dipping Glenfiddich fault on the right. So the E42 mine stratigraphy is this succession here that Matt sort of discussed in his presentation. And the main issue with making correlations is that below the Muddy Lake diorite, this pink unit, the stratigraphy underneath it is dominated by this monotonous facies of massive fine sand that just generally lacks clear marker beds. So as you progress to the east, this wedge between Cowal shear and Glenfiddich is dominated mostly by diorite. So you sort of lose your stratigraphic context for extrapolating the E42 stratigraphy out east towards the GRE46 deposit. So there's also more deformation as you go out to the east and less drilling as you get away from your main ore bodies. So those are the issues with doing volcanic facies correlations at Cowal. So those are the issues as I'd understood it when I started this project. And the aims were therefore to delineate the stratigraphy with an initial focus on GRE46 and to go further afield, if possible, to the gold corridor and the Cowal igneous complex. Interpreting eruption processes, transport processes, and paleo environment is an obvious research aim because this is a volcanology project. And integrating that sort of understanding with previous studies, interpreting the volcano-magmatic evolution of the Cowal complex has a natural follow-on with previous studies that have been done at Cowal on ore deposits, the metallogeny, and intrusions as well. And where possible, extrapolating out to the Junior Narromine belt and the Macquarie Arc would be great, if possible. So to achieve those goals, basically a lot of logging was done. Logging coverage was seen as the way to get there. So this is a northeast isometric view of the most recent geology interpretation, and you can see where the E42 pit is indicated. All the red lines are the holes that I've logged, and I did fieldwork at Cowal from April to October last year, and in total there's about 27 kilometres of detailed logging. There's lots of photographs and samples, and GSNSW has kindly done 55 standard thin sections from those samples so far. Note also that I logged blind with an RTP magnetics map as my reference, so I only started looking at this geology interpretation when it was time to, when my own work was advanced and I felt like I could incorporate other interpretations. So what's pleasing is that this work so far has independently validated this geology interpretation. There's an example of the detailed logging on the left. So it's 100 meters to an A4 page, and it works out to be approximately 1 to 500 scale. The map on the right is highly detailed, but it can be simplified. So firstly, the Muddy Lake diorite is in pink, and there's a granite diorite batholith in beige as well. Subdividing the Cowal complex, starting from the east, is this structural domain characterized by open folding. The next domain to the west is dominated by thrusts, and then the westernmost domain is the gold corridor stratigraphy. Here's a hypothesis to consider over this talk. where I'm sort of relating the structural styles of open folds, thrust, and gold corridor stratigraphy to the stratigraphy and the rheology within those domains. So we'll start from the east, we'll look at the stratigraphy within each domain, and this is the cross-section that we'll do it on. So it's a northwest to southeast cross-section. So here it is. You can see on the section the domain of open folds to the east, thrusts in the center, and then to the west is the gold corridor stratigraphy. And for now, just note the granodiorite at the bottom right of the image, and then above that's a thrusted block of granodiorite, and above that granodiorite thrusted block is your domain of open folds, and then as you progress out to the west is your remaining stratigraphy above that granodiorite batholith. Just a note on these lines in red now, these are 3D surfaces in Leapfrog, but they are based on digitizing the regional seismic lines that were done by GSNSW in 1997 and 99. So in the next slide, we'll look in this area, in this red box here, which is effectively the remaining stratigraphy above and northwest of the granodiorite, and the E42 pit is shown there for spatial context. So here's the stratigraphy. You can see how the graphic logging coverage was vital in describing facies and delineating facies associations across major faults. So again, we're going to work from east to west, discussing the stratigraphy within each of those major structural domains. And once again, as we do that, keep in mind this hypothesis of the relationship between stratigraphy and structural style. So for a few of the following slides, what you'll see is the stratigraphic columns on the top left. At the top in the middle is a blown up view of the stratigraphy for the structural domain that we're discussing, and then at the top right's just my talking points essentially. This domain of open folds is dominantly effusive basalt and andesite, and from cross sections it's estimated as being approximately 600 meters thick. So the effect of shortening hasn't been quantified yet, but perhaps the open folds in this domain and how gentle the deformation is compared to the west has something to do with the mechanical strength of having such a thick effusive sequence. However, recall also that the granodiorite batholith is about there on that cross-section to the top left. So alternatively, that's the big rigid body that has buttressed strain and is responsible for the gentle open folding in this domain. Stepping over to the west is the structural domain of thrust, the lowermost unit here being this coherent pyroxene basalt substrate. Note that that's alteration-induced pseudo-breccia textures. It's locally reworked at its upper contact, and then above that position is a period of quiescence with mud, intruded by effusive basalts that starts off initially as a pepperite and possibly transitions to a lava. Locally, in that stratigraphic column, there are scoria breccias as well, but because they're monogenetic with limited footprints, they have limited utility for basin scale correlations, so we'll sort of skip past that for now. Going up stratigraphy and west in the next domain to the gold corridor stratigraphy. The lowermost unit in this domain is interpreted to be this massive to laminated dark sand. So this is that monotonous ubiquitous facies below the E42 mine stratigraphy that lacks obvious marker beds. So this is the rock type that has a lot of problems for correlations, particularly when you deform it. And eventually you get to the mine succession of breccia conglomerates, trachyandesite and Fiamme breccias, and I'll probably just skip past this. And anyway, the point I was going to make was that I'll ignore the E42 mine stratigraphy because it's well documented and has been known about since the 90s. So we've sort of looked at this cross-section, and I just want to make a point about how the diorite might play a role in the change of deformation style in the hanging wall to this thing called the reflector fault. So on this section, again, your domain of open folds to the east, your thrust position, and then your gold corridor stratigraphy. On the cross-sections that I was working on, you can interpret an antiformal fold to the diorite and the hanging wall to reflector, and that brown squiggle is east vergent parasitic folding of coarse breccias in the hanging wall to reflector. Here's another west to east section about several kilometers to the north, and the only difference, like both sections are pretty much the same, the structural domains are the same, and the broad stratigraphy is the same, but what is different is the structural style in the hanging wall to the reflector fault. So in the south, we have an antiformal fold to the diorite. To the north, the diorite actually thins out as you go to the north, such that it doesn't buttress strain anymore, and you have thrust repeats rather than this antiformal fold there. So is the diorite a factor in this change in deformation style to reflector, in the hanging wall to reflector rather? And that's, I'm not a structural geologist, but this is the preliminary sort of structural framework that I've got, just because it is ultrastratigraphy and there's a lot of orogenies that you have to deal with, but that's the language about the structural domains that I was talking about: open folds, thrusts, gold corridor stratigraphy, and then the facies and rheologies within each of those domains. So the succession seems to be consistent across major structures, and it poses this interesting question of the relationship between structure and stratigraphy. You have this chicken or egg scenario where is the structure controlled or an effect of the rheology of the facies, or are the facies controlled by early structure? At this point, I'm inclined to think that that's more of a factor, like both things will be at play, but perhaps, this is early basin architecture. It's got a lot to do with the distribution of facies through the field. So I think reflector might be an early growth fault that's been reactivated essentially. And here's a list of things to focus on for the next 2 years. And the first thing to do is to see if you can model it in leapfrog essentially, test it in 3D. Validation of the facies architecture with thin sections in geochemistry is ongoing, and zircon uranium lead dating of the stratigraphy would be a great thing to accomplish as well. And that concludes my update on the volcanic facies architecture. And thanks to these people at Evolution Mining, the Geological Survey of New South Wales, and my supervisors, Martin Jutzeler, Rebecca Carey, and Ray Cass. Thanks very much.